In this video, I want to define what we mean by the order of an element in a group. To get started, our basic definition is going to be the following. Let's let G under star be a group. And as always, A is some element of G. Then we're going to define the order of A inside group G to be the following. The order is going to be the smallest positive integer named k such that a to the k is equal to e, where e is the group identity element. Now, there's a couple of things that I want to point out about this particular definition. First of all, we are going to write the order of A is equal to K. So this particular syntax is going to be the order of A. Yes, that is reusing absolute value syntax from lower level mathematics classes, but absolute value is not going to raise its head in abstract algebra. And so it's important to get to where you're reading this kind of a statement as the order of A is equal to K, not the absolute value of A. And the next thing that I want to do is I want to actually make sure it's clear what I mean by the smallest integer, such that this is true. So when we write the order of A is equal to K, we actually mean two things. First of all, yes, A to the K is going to be equal to the group identity element. But the second thing is we also mean that if I take an integer L that is positive, so it's bigger than or equal to 1, and it is smaller than K, then I also know that A to the L is not going to be the group identity element. So when we say that the order of an element is equal to K, both of these things are true. Now, the next thing that I want to observe about this definition is that this definition is written in multiplicative notation. We're thinking about stars behaving like times, and so we're looking at powers of A, and powers of A represent A star A star A star A. So it's looking like multiplication. If we have an additive group, the order of A is defined in the same way, but we have to translate this whole definition from multiplicative notation into additive notation. So let's look at what that would look like. If I have an additive group G, then the order of A is equal to K means the following two things. First of all, it means that K times A, which is a repeated addition where we have K copies of A, is going to add up to be the group identity element. And the group identity in an additive group is usually written with a 0. So this symbol here is simply the identity element for our group G under plus. And the second thing saying that the order is equal to K in an additive group means is that if I look at L times A, and that would be A plus, where I have L copies of A added together, whatever that is, it's not going to be the 0 element. So that's how the notation works in both multiplicative and additive groups. There's another comment that I want to make before we start looking at examples. If we are in a multiplicative group and A to the K is never equal to E for all K's that are positive integers, Then we are going to say that the order of A is infinite. In an additive group, this statement would look like if my group is additive and k times A is never equal to the 0 in the group for all positive integers, then I would be saying that the order of A is equal to infinity. We can also say in both of these situations that A has infinite order. That means the same thing. So now let's look at some examples. In my first example, I want my group to be the group of units mod 8, and that is a group under mod 8 multiplication. And what I want to note is I want to note that 3 is inside the group of units mod 8, and I know that because the GCD of 3 and 8 is equal to 1. And so what I want to do is I want to find the order of 3 inside this group. Well, the easiest way of finding the order for a specific element is literally to just pile up its powers since we are in a multiplicative group. So I'll look at 3 to the 1. That's just 3. I look at 3 squared. That is 9, which is congruent to 1 mod 8. So 3 squared is the same thing as 1 inside my particular group, and that means that the order of 3 is equal to 2 inside the group of units mod 8. Well, let's look at another example. This time I'm going to look at Z12 under its addition. And again, I want to make a note that 3 certainly belongs to Z12. And so I want to find the order of 3 inside Z12. Now Z12 is written additively, so instead of looking at powers of 3, I'm going to be looking at multiples of 3. So 1 times 3 is just 3. 2 times 3 is 3 plus 3, that's 6. 3 times 3 is 3 plus 3 plus 3, that's 9. And 4 times 3 is 3 plus 3 plus 3 plus 3, which is 12, which is the same thing as 0 when I'm thinking about all of my addition being done modulo 12. So the arithmetic here is in mod 12. And what this last statement says is that the order of 3 is going to be 4 inside the group Z12 under its addition. Well, let's look at one more example. I also know that Z itself under addition is a group. And 3 is clearly an integer. Now, what I want to notice in this particular thing is I want to note that inside Z, I know that 3 times k equals 0 implies that k has to be 0. So, if k is a positive integer, then I know that 3k is never going to be equal to 0 inside the set of integers underneath their addition. So inside the group of integers underneath their addition. And hence, what that tells me is that the order of 3 is equal to infinity inside the group of integers underneath their multiplication.